We've treated the moon as a documented archive, a static, lifeless rock cataloged down to the meter by decades of robotic observation. Orbiters like the LRO and Chandrayaan-2 have spent years mapping these craters with digital precision. Based on their data, we believed we possessed a complete record of the lunar environment. The Artemis 2 mission changed the input. For the first time in over 50 years, we sent human biological sensors, the crew of the Orion capsule, back into the deep lunar environment. During the mission's closest approach, the capsule swung behind the far side of the moon. For 40 minutes, the crew was plunged into a total radio blackout, cut off from all contact with Earth. When the signal finally returned, astronaut Christina Koch didn't describe the sterile gray world the probes had recorded. She called the far side a living, breathing chaos, an observation that didn't match the digital files waiting for her back on Earth. Why did our satellites record a monochrome world while the Artemis crew saw a vibrant one? This diagram shows the logic of a digital orbiter. To eliminate image noise and save data, the sensor averages out subtle color variations. It optimizes the image for topography, but in doing so, it frequently renders a complex landscape as a uniform gray. The human eye has a significantly higher dynamic range. When the sun hit the surface at a specific angle, Koch reported seeing rich browns and distinct fields of green across the lunar soil. That green indicates the presence of olivine, a heavy mineral usually trapped deep within a planet's mantle. To see it on the surface means that ancient impacts were violent enough to turn the moon's interior inside out. The gray moon we know is largely a result of digital compression. By simply being there, the human eye detected a chemically rich history that our machines were programmed to ignore. Pilot Victor Glover reported another visual anomaly: sinuous, geometric squiggles near the Reiner Gamma region that looked like they had been traced onto the ground with a brush. Our algorithms previously classified this area as a flat magnetic anomaly, but under direct observation, Glover saw a pulsing, layered structure that changed as the sunlight hit it. These discrepancies were most visible at the terminator line, the border where the lunar day meets the absolute darkness of the night side. In this high-contrast zone, Glover saw a symmetrical double snowman crater and mountain peaks suspended over a bottomless void. This is a histogram of a digital sensor at the terminator. Because the contrast is so extreme, the camera crushes all shadow data into a single black block. It loses the ability to perceive depth. Humans use intuitive spatial awareness to decode these shadows. Where the digital network sees a flat image defect, the human brain perceives three-dimensional depth. Glover also spotted impossibly bright newborn craters and massive cliff edges that looked like they were actively drying out and settling. These are lobate scarps, active tectonic fault lines. As the moon's hot interior continues to cool, the entire satellite is physically shrinking. Much like a piece of fruit drying in the sun, the lunar crust is buckling and wrinkling as the core contracts. These observations indicate that the far side is not a dormant relic. It is an environment experiencing moonquakes and tectonic shifts right now. These geologic observations change the logistics of lunar colonization. The green olivine Koch identified is more than a curiosity. It is a source of oxygen and magnesium. Finding these deposits on the surface means we can mine life-sustaining materials locally instead of shipping them from Earth. The magnetic squiggles at Reiner Gamma actually deflect solar wind. These structures could act as natural radiation shields for human habitats. However, the active lobate scarps mean that any future colony must be engineered to survive frequent and violent moonquakes. The data gathered by the Artemis crew proves that surviving the moon requires dynamic adaptation to a chaotic, shifting environment. Robotic probes are efficient. They don't need oxygen, they don't get tired, and they can send data from radioactive zones that would kill a human in minutes. The Artemis crew, meanwhile, had to troubleshoot a frozen space toilet and manage floating jars of Nutella while isolated in deep space. But remember Harrison Schmitt on Apollo 17? He used raw intuition to notice a subtle change in the texture of the dirt, leading to the discovery of orange volcanic soil. A machine is programmed to follow a specific path. It is unlikely to deviate to investigate a patch of dust that wasn't already in its mission log. Space exploration isn't just about data points. It is about the ability to improvise when a system fails and to recognize significance in a visual anomaly that a sensor would average out. Without human perception, the moon is just a high-resolution file. With us, it becomes a place where we can actually